Communication Engineering at GM University. In this video, I will be presenting a project that is part of our technical competency course, and the topic is MOSFET ID versus VGS and ID versus VDS characteristics using LTspiceSimulation software. This experiment helps us understand how the drain current in a MOSFET responds to changes in gate source voltage and the drain source voltage, which are fundamental to the working of MOSFET in analog and digital circuits. So let's move on. Let's move on to the circuit diagram. I have plotted a circuit diagram here. So you can see here I have used one NMOS transistor. Then I have used two voltage sources, one for VGS and another for VDS. Then I have used two resistors. One is connected to gate terminal and another one is connected to drain terminal. And the source terminal is made ground, and negative terminals of voltages are made ground, that is common ground. And I have kept value 10 volts and the VDS as 30 volts, that will be constant. So in first case, ID versus VGS. In ID versus VGS, we need to keep VDS constant and we need to vary VGS. So we will start the simulation. So here we will go to configure analysis. Here we need to go to DC sweep. In DC sweep, we need only first source, that is VGS. So let's type VGS. Then type of sweep, that is we need a linear. Start value will be 0 from where we want to start, and stop value will be 10 or what else you want you can keep. Then increment I will be keeping 1. Then as follows, you can see I have stored the VGS DC sweep in steps of one steps increment. This helps us how the MOSFET turns on as VGS increases beyond the threshold voltage and how ID increases exponentially in saturation. So let's run this circuit. Let's see the current here. Yeah, you can see the graph here. You can see it is incrementing step by step, that is one step. From 0 to 1 it is slightly increasing, it is not increasing, it is 0. From 1 to 2 it is increasing, from 2 to 3 it is increasing, slightly it is increasing stepwise. I will make you mark the data points how it is increasing. See, from 0 to 1 it is not increasing, it is 0. From 1 to 2 it has slightly increased in the current. Below threshold ID will be 0. As VGS increases with respect to threshold voltage, ID increases significantly. Then we say the MOSFET is turned on. ID increases quadratically in saturation region. So this is about the first case, ID versus VGS. So let's move on to the ID versus VDS characteristics. In that, we need to do VDS. We need to make VGS constant and make VDS vary. So let's again go to DC sweep. Here first source will be VDS. Type of switch will be same, linear. Then start value is 0 and stop value I will keep it as 30 or 20. Increment I will be keeping it to 2 or 0.8 or something. This is about VDS. Then we need to keep second source will be VGS, as we are keeping it constant, 0. I will show you both 0 to 10. Increment I will keep same, 1. Okay, as you can see, I have inserted the values, that is for VDS I have start value is 0, stop value will be 20 and 0.8 steps. It will increase step by step, that is 0.8. This simulates ID versus VDS curves for different fixed VGS values. VGS value is fixed and VDS value will be varied. Let's run this. Let's see the current here. As you can see, the variety of graphs we are observing. At low VDS, the MOSFET operates in the ohmic region and ID increases linearly. You can see linearly. After a certain VDS, MOSFET enters the saturation region. From here, it will enter a saturation region, and ID will be constant. It won't change when 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 it enters a saturation region. Each curve corresponds to a fixed VGS value. Hence, this is the graph of the second case, ID versus VDS characteristics. MOSFET in generally MOSFET conducts only when VGS is greater than threshold voltage. In saturation, ID is controlled by VGS and almost independent of VDS.